Let's make a start. Let's see, did I get all the... Yeah, I did get all the screen shares. Cool. If you saw the schedule for today's class, I have since realized just now that there is now a clash, more or less, that we are covering the same things in the same classes. This would have been a full overview of all of probability, but because we literally just sort of looked at probability stuff before, what I think will be a good idea is to cover the statistics for discrete that we didn't get to do actual examples of before. So I'll very briefly touch on what those were again and how we calculate those, and then we'll dive pretty quickly into the questions regarding that. So for discrete probability, we're usually using these probability tables, and that will be the case for all of our the statistics that we calculate for this. You'll always have some sort of probability table, or you'll have to find a probability table to use. Calculating the mean, or otherwise known as expected value, sometimes you'll see the letters e of x, sometimes you'll see the Greek letter mu. Both of those mean the same thing. They mean the average value of the data set. The way you calculate it is by going column by column. You multiply the results in each of the columns, and then you add everything together. So that would look like 0 times 0.216, 1 times 0.432, 2 times 0.288, and then 3 times 0.064. Then you're just going to add all those together, thus getting you the mean. This tells you, the fact that the mean is 1.2 tells you that the average result is 1.2, slightly skewed right of 1, which should make sense given that most of the probability is located at x equals 1, and a decent chunk of it is slightly to the right of it. If you have to do e of something other than just x inside of the brackets, the most common of which is e of x squared, all it means is that you square each of these x values before you, all it means is that you do whatever's inside the brackets as a transformation to that x value before you do your multiply. So if we have a look at the e of x squared version, it would be 0 squared times 0.2, 1 squared times 0.15, and you can see all those are listed below there. That result there, e of x squared, is used in calculating the variance. It's one of the first things you need. You need e of x squared, and then you need to find the regular mean and then square that result. Both of those are different things. So you've seen how that one works, and you've seen how that one works. All you need to do is square that result. Won't worry about that. And then lastly, standard deviation. So that's always going to be the square root of variance. So that calculation of e of x squared minus e of x all squared, all you're going to do is square root that result to get your standard deviation. What variance and standard deviation are measures of spread. They tell you how far apart the data or the probabilities of any given event occurring are spread across the data set. If we have a look at the table that we have here, this would be fairly low variance. A decent chunk of the probability is located on one particular outcome. And so that brings us to confidence intervals, which basically tells us what's the percent likelihood that our result that we're looking for is between plus minus a certain number of standard deviations. Most common of which is a 95% confidence interval, which just means that you are 95% sure that your value is going to be between plus or minus 2 standard deviations. So that means you have to calculate your standard deviation, which means you need both the variance and well, I guess you just need the variance, but variance also needs mean. So you calculate your 3 statistics, and then you plug them into your into that set of inequalities, and that gives you your result. Worth pointing out once again that for small data sets, this is pretty nonsensical. It doesn't really make sense to have a boundary of negative 0.23 to 3.23. This will become much more applicable when your data set is larger, although truth be told, it doesn't really come up in, well, they don't usually give you massive data sets in at least having to do it by hand. Let's see, actually, this one gave you 10 different results, so not great, but doable. Do I need to double click into any of how we calculate those again? All right, sweet. Let's give them a shot. So question 1 of 13D, we'll have a read of. Should be a little bit of revision from last class. Where basically all we're trying to do initially is create our probability table. So I'll start drawing out the framework for it, and then someone can tell me how I actually populate it. Yeah, if you were in the last class, this question does have a slight nuance on it as opposed to the last time we did this. Keep that one in mind.
So Chris, would we want to like establish our winnings first?
Establish our winnings. Correct. Yeah. What are the net winnings? Those will be the...
So you have a 30% chance of breaking even.
Yep.
You have
30%.
a 10% chance of gaining $18, and then 60% chance of just losing $2.
Yep. Let me just double check all those once I have this written down. 10% chance of winning 20, and then you subtract the 2, yeah. And then otherwise losers, so 60%. So you've lost $2. Yep, that all checks out there. That fills out our table, at least of the values. As far as how you would fill out the rest of the columns, you might say like, I don't know, $X, and then PR. Yeah, even just X is fine. No need to make it overall complicated. You'd say PR capital X equals little x, and that would fill out the rest of the table for that. Cool. Now, that actually wasn't the question though, but it was required to solve. We do need this table. The question is, how much might you expect to win or lose if you play this game 100 times? That's a bit more to think about, and it is applicable to what we just briefly covered. You got a screenshot of how it all works, by the way, in the chat.
Chris, would you expect to win $60 overall?
Expect to win $60. I didn't calculate it. Let's find out. I'm gonna have a look for it. Yes, $60 is correct. So, what'd you come to that conclusion by? It is correct.
I just went row by row with the winnings. So
Mhm.
the breaking even one doesn't really matter, so you just disregard that.
Yep.
And then since you have a 0.1 chance of winning 18, that's 10 times you're gonna win $18. So that's $180
Yeah.
of winnings. And then since you have a 0.6 chance of losing $2, that's 60 times you're gonna lose $2. So you lose 120, and then like your profit is $60.
Yeah. No, fair enough. That's so. What you've effectively done is break that up into multiple stages rather than doing it all in one line, which is perfectly fine. Just so I can get it all on paper. Basically, what goes on is you do the expected value, so the mean or average, which is the 0 times 0.3, which is why I said that can be ignored because that's obviously just 0. Then you've got the 18 times 0.1, which is that column. And then lastly is the 2 and the 0.6. And then that gives you some result, probably 6. If I take a, well, actually, it'd be 0.6, wouldn't it? Because you've got to multiply this by 100 because you're doing 100 games in total. Let me just double check those numbers. Yeah, 100 games in total. So when you multiply all that together and do your addition subtractions, that'll give you 0.6. And then in total, you're running 100 games, so you're getting 100 of these 0.6s, getting you $60. The way he's described it is he's just done each of these individually and multiply them by 100 before, rather than add them up and then multiply by 100. Same thing. Anything to clarify further on how that one works for anyone? Okay. That kind of sets us up pretty nicely to solve all of question 2. You're just doing exactly what I just did there, but there is no like final multiplication afterwards because you're only doing it based on one of these. There's only like one iteration of it. It's not saying like how many times you run through this table. Whenever it says just find the mean, you're assuming you're running through it once. Same vibe there. Same vibe there. Let's see. Do we have anything that's not the mean anymore? Yeah. It's still the mean, but this one seems complicated enough that it's worth having a think about. Question 6. This one is going to be an exceptionally long table. So even if we just think about the possible outcomes first, that'll be a good starting point. And if it's hard to imagine all the possible scenarios, could anyone describe to me one possible scenario that could come up in this game? Like one result that could happen?
Getting a 7.
Getting a 7? Yeah. How does that happen?
She gets a 6 and then she rolls again and then she gets a 1. So she adds the two numbers together.
Yeah, correct. So all I'm trying to like field there is that you guys understand how the game works. So if you roll a dice, any numbers from 1 to 5 means you don't roll again, and that just becomes your number. But when you roll a 6, it means you now have to roll additional dice and then add to that. So now that it's clear what the actual game is, we can now consider all the results, which I've kind of given a hint for the first set of results, but yeah, continue having a think of the rest of the ones.
Chris, I know the answer.
Oh, the flat out answer at the end. Okay, that's
Like
impressive.
for the like probability distribution table.
Yep. Okay, there is a lot of things there. Is that where we spent all the time doing the whole thing? Nice.
Yeah, like so up to like the number five, right? It has a probability of 1/6 for all
Yeah.
those five numbers.
Yep.
And then you can't have six because if you roll six, you're gonna add something to it. So six is like you know how like six would have had a probability of 1/6, but instead you further divide that by six, and then a lot from 7 to 12, you give it each 1/36 as a probability.
Correct. Yeah. So 6 cannot exist because it's not possible. You roll a 6 and then you add something, which is why we now go 7, 8, 9, 10, 11, and then 12, because 12 being the final one because you've got 6 and 6. And then, yeah, because you're rolling 2 dice in sequence, the rest of them is going to be 1 out of 6 times 1 out of 6, which would mean 1 out of 36 for the rest of those. Yeah, that's how you do the full table there. This is not something you'd have to do in an exam, by the way. This is way too many elements. The most I've ever seen is 4 on a single table. But yeah, it's good that even with this large sample size, you're able to still fill out that table relatively easily. Yeah, those are the outcomes. As far as then finding the mean of that, I don't really need a number for this because at this point, well, you do need it for the actual question, but like I get that you guys probably get this, which is once you have your table, it's just 1 times this, 2 times it, 3 times it, 4 times it, and then you move on to the 1/36s, and you just add all those together. Lots of adding, lots of multiplying. It's really just crunch the numbers, so we can leave that there. Where it does get a bit different is question 7. Specifically, the only one I'll touch on would be part B. So I'll put 7b in the chat. E of x cubed. So if that looks, actually, do I have that even in my screenshot? Don't really. Let's yeah. Does anyone remember what happens if you got like stuff on the x? What does that actually change about what you do?
Can we like apply that rule to the top numbers?
Yeah, to the top numbers. Exactly. So when you have e of x cubed, what does that mean? What does that actually overall change about calculating the mean here?
Does it mean just also get cubed as well?
The mean itself doesn't get cubed. That would be as if I had said, so if I draw this out on the document camera, that would be as if I had said e of x all cubed. That would cube the mean. Whereas when you have e of x cubed, that's what you're talking about before, which is all the numbers in your table would get cubed before you multiply them by their probabilities, and so on.
Right, so like when you're just multiplying it by p of x, you just gonna cube the x and then
Yeah, correct. So for this one here, it would be if you look at not the document, the textbook, it would be 2 cubed times 0.01, 3 cubed times 0.25, 4 cubed times zero point 0.4, so on and so forth. Same sort of deal with all these other arithmetics, although the only one you'll actually ever care about will be e of x squared. Not even e of x cubed, but it was close enough to where it was worth pointing that one out. Okay, that's that. Anything to clarify further on that? If not, we can start working on question 9. And yeah, just interrupt me at any point if you do want me to clarify what's going on. More than happy to go back on a question. for those who are still working on 9a, consider the fundamental rules of the probability table. What has to be true?
Chris, is 9a just p is equal to 1?
P equals 1 is a little bit big. What was the reasoning behind P equals 1?
Because I just saw that like the fraction was like continually getting divided by 2.
Okay, so you saw a pattern and you're like,
So I
yes.
thought that maybe if 1 and like divided by 2 is equal to 1 over 2.
No, I like your idea in the sense that you saw the pattern and you're like, yeah, gotta be 1. Um, that is good reasoning. You'd be actually well suited for special math in that case because they do a lot of those pattern seeking sort of things. But in the context of a probability table, there's a couple of fundamental laws, one of which got broken by what you just said. Can you think about what's been broken by setting p equals 1?
The probability exceeded 1, the total
Yeah,
probabilities.
the total probability exceeded 1. So everything in this table has to add up to 1. That's not only is that a law for all probability tables, but it's also just how you solve this question. Everything in here has to add up to 1. That means p is the only thing left in the equation to go from there. But just for the sake of it as well, the other law is that any individual probability has to be between 0 and 1, or at least in such a way where it all adds up to 1 at the end. That law wasn't broken because setting this as 1 isn't inherently wrong. It's just that there was other entries in the table. Yeah, so just to write out what that might look like, you would have all the probabilities in table need to, 1 out of 16. Let me double check. Is that what we get? Yeah, ends up being 1 out of 16. So what that looks like written out is you have your probability p plus your probability half plus a quarter plus a eighth and then plus a 16th. That all has to equal 1, and then you just rearrange for p, which is going to give you 1 out of 16. And then for e of x, you've got e of x equals 2, which is also correct. Yeah, because once you have this table, you've got your p value, and so it's just 0 times p, 1 times half, 2 times quarter. And so, yeah, that gets you your e of x equals 2. Nice. Now, is it on the screen share? It is. Not on the screen share, sorry. On the screenshot, you do have the equation for variance in there. So you need to find 2 things to calculate this variance. If you need me to jump in, let me know. Otherwise, enjoy. Missed out on how to find e of x for this specific question or just in general? For this question? Yeah, so for this question, p was required for finding e of x because you got to do your it's the mean, right? And so you need what all those probabilities are. If you solve what's on the document camera, where all the probabilities have to add up to 1, that is going to get you p equals 1 over 16. And so your table now looks like you got 0, 1, 2, 4, 8, 1 out of 16, half, quarter, eighth, and 1 over 16. You're now just doing e of x like you normally would with this table. So 0 times 1 over 16, 1 times a half, and so on and so forth for all those values. And then when you add all that together, you get 3. Oh, sorry, 2. I misread that. Is it clear enough how you go about that now? Sweet.
Chris, is variance x like 7/2?
Variance x 7/2. Yes, it is. Hell yeah. And so the way that works for everyone, once again, I've got the table. Variance is, so var x is the same thing as e of x squared minus e of x all squared. So we had e of x from before, that's just 2. So the term e of x all squared is therefore just 2 squared, so 4. And then for e of x squared, it would just mean that you go back to this thing we were doing here, which is adding all these up, but you put a square on each of these. And that gives you e of x squared, which would have been some fraction. Then all you do from there is, well, you just perform that subtraction. You want to do whatever this result is minus the 4. And that's going to give you, what was the value again? It was 7/2. So final value for variance would have ended up being 7/2. Do we need to see that in any more detail? Let me know and I'll write it out. Otherwise, I'll find another question. What's going on in 10? Bias die, X's score, probabilities K are... Yeah, I mean, we won't do like everything in 10. You can if you want, but the only unique part of this besides what we just did is the 10A section. So let's have a go at 10A. That'll be a fun one. This will be like the main point of contention. If you can understand what that means, then you'll be sorted. Otherwise, it'll be a bit tough. So have a think about that specifically. Anyone have any thoughts on what that statement might have meant? PR x equals R equals KR. Start writing something out and maybe it'll make sense. Yeah, x equals R, and then 5, 6. Those are all the R values that we were told. And we're told it equals KR. I think that's as far as I'll write that before. Otherwise, it'll give it away if I just start writing what's in here. Basically, there's a way to figure out what's in all of these spots. And it's based on that statement, which is PR x equals R equals KR. This thing helps you with whatever these are. I'll give it another minute or so.
Can we just substitute like K, 2K, 3K?
Yeah, absolutely. So this statement here just says the probability that x is equal to some value r is equal to k times that value of r. So if r is 1, then you have k times 1, or just k. If r is 2, then you have k times 2, so on and so forth. 3k, 4k, 5k, 6k, and then once again, solving this is no different to how we solved the previous one. Previously there was 1p in the equation, this time there's 6 different k's, but fundamentally it's the same sort of idea, which is to what? How to get k from this?
You add it all up and then divide. Like you equate it to 1, and then you're gonna get like K is equal to 1 over 21, I think.
Yeah, 1 over 21. Let me double check that. Yes, 1 over 21. So yeah, exactly the same thing. Everything in a probability table has to add up to 1, so you add it up to 1 and then solve for k. Nice. Okay, that's that one. Let's see. Is there anything else that's actually real interesting to have a look at? Unbiased die. A regular tetrahedron. Nice. Die stone. 2 multiply. Yeah. The unique thing here would be the labels of the columns. Yeah, why not? We'll do one more of these where you have to figure out what the columns are going to be labeled, and then I'll find something else. So don't need the full table if you don't want to have the exact full table, just what the elements on the top would be. Probability has a way of being the exact same question every single time, but worded sufficiently differently to where you feel like you're doing something different. Because yeah, fundamentally it's the same sort of idea, which is figure out what the columns are and then probabilities of outcomes, but it's all in the wording. It's both the blessing and the curse of probability, where it's all extended response. The blessing in that is that there's only so many ways you can word something. So when you've seen it all, you've seen it all. But you have to have seen it all. Are we having trouble with how the game works, or are we just thinking about how to calculate number of combinations, or what the combinations are? Or maybe just a quick, if you're working on it reasonably well, just thumbs up for me so I know you're not just really stuck. Maybe we are stuck. Okay. So what's going on here is you've got this basically a four-sided die. And so you're throwing the die, and whatever this is saying, basically it means you roll a die, you get a particular outcome, any number 1 through 4. Now, you're not just rolling one dice, you're actually rolling two of them, and the score is found by multiplying those two things together. So one possible outcome could be I roll my two dice rather. One of them is a 2, one of them is a 4. My net result is going to be an 8 because you multiply the two things together. That's how the game works. The question now becomes, how do I calculate the number of, or what those actual combinations are? And even the number of combinations is also appropriate. We've done this before in probability fundamentals, which is when you have a two-stage experiment, there's a couple of things you can do. One of them is a tree diagram, and the other is a two-way table. This one here would be better sorted with a two-way table because you only have two outcomes, and it's typically better to fit things in a grid than it is to fit things in a sequence of branches. Because this one, I believe, 4 4s are 16. Yeah, it's going to have 16 branches if you were to do a tree diagram. Not great. So, the way it works, you're going to have one row, which is all the possible outcomes of, let's call it dice 1. Then you're going to have a column, which is all the rows, or all the outcomes of dice 2, which I've butchered. Let me fix that. 1, 2, 3, 4. And then in each of the individual cells, that'll be messy actually. In each of the individual cells, what you do is you put the product. So for instance, the 1 and the 1 just means you rolled a 1 on both die, multiply together to give 1. 1 and 2 makes 2, and you can very quickly fill out a lot of these. 2 and 2 makes 4, 3 and 2 makes 6, 4 and 2 makes 8, and since it's symmetrical, you can leverage what you did horizontally. You can do the exact same thing vertically. 3 3s are 9, 4 3s are 12, and then 4 4s are 16. That gives you all your possible outcomes and even some duplicates. Like you can see, you got 2 and 2, you got 3 and 3, 4 and 4 and 4. You got a bunch of different duplicates there. So looking at that list of combinations, when you create a probability table, you would pick all the unique ones, which is there's a 1 there, there's a 2, there's a 3 and a 4, there's no 5s, there is a 6, there's no 7s, but there is an 8, there's a 9, a 12, and a 16. 9, 12, and 16. So that would be how you'd end up creating the table on that. Obviously very big, but point being is how you could create a table. Now, the next stage would be how to calculate probabilities, but for now, is there anything I need to clarify about how I've gone about that? I'll pause for a couple seconds. Okay. Now, to actually calculate these probabilities, have a think about that. How might you, based on what you're seeing here, calculate probabilities for these outcomes? I'll zoom in mainly on this table itself because that's going to be important. How might we calculate probabilities?
Chris, would you look at how many times that individual number appears on the table? And since there's 16 outcomes, you just create a fraction out of 16?
Bang on. Absolutely right. Yeah. So probability of 1, it only shows up once out of 16 outcomes, and so it's going to be a 1 out of 16 chance. 2 shows up twice, 2 out of 16, or just 1 out of 8 when simplified. The reason that works is because each of these are equally likely. It's unbiased. There's no bias in the die. None of these are weighted more heavily than another. If they were weighted, geez, what would you do then? Then you'd have to force yourself to do a tree diagram. Yeah, because like if you've got numbers 1 through 4, but let's say 4 is heavily weighted, you've got your 1, 2, 3, 4, 2, 3, 4. Let's say that's got like a 5 out of 10 chance. This has got a 2 out of 10. This has got a 1 out of 10. What am I left with? 5, 6, 7, 8. And then a 2 out of 10. The only way to go about this would be full tree diagram. We then do another set of 4 branches off this, another set of 4 branches off this. The good news is you wouldn't like physically draw that. You would really only need this first one because this just repeats. Because, well, assuming both dice are weighted the same way, this would just be one iteration of dice 1, and then you just copy that over 4 separate times over here. So you might as well just stick with what you got here. So for instance, the probability of rolling a 1 then a 1 would be a 2 out of 10 times a 2 out of 10. Whereas a 1 then a 4 would be a 2 out of 10 and a 5 out of 10. You can just use that instead. Clear enough on how you might do it if it was a biased die, like I've just depicted there. Okay, that's that one. Moving on to something else in the book. A lot of this is kind of repetitive. Yeah, that's all that. Nice. All right, so that's all. Those are like the fundamental questions, or a bit beyond the fundamental questions that come up with the statistics. What we can now do is look at statistics for binomial. Maybe very briefly, I'll talk again about what binomial actually was. So binomial was basically the special kind of discrete, which had 3 specific criteria. You needed to only have 2 possible outcomes for a given scenario. So coin toss being like a head or tail is a good example of that. Repeated trials have to be independent. So that's kind of like what I mentioned before, which is that repetitive dice throws don't have different probabilities from trial to trial. It's not like they get dented and they change their weighting, although maybe in the real world technically they ever so slightly would. Maybe, I don't know. And then probabilities don't change from trial to trial. These are usually thought of as the same thing, but mathematically speaking, these are ever so slightly different. The difference doesn't actually matter. You don't need to know the nuance about that. The way we calculate binomial probabilities is with the Bernoulli sequence. So you'll notice this equation at the front from when we did counting methods. That is the selections equation. And then from there, it's just how many successes do you have and how many failures do you have. So P is probability of a success, and then X is number of successes. And then failure, well, if you either succeed or fail, then failure is going to be 1 minus the probability of success. And then whatever that power is just how many times you failed in the experiment. So the quick example would be, you toss a coin 5 times. If you want to toss 4 heads, that means N is 5 because you're doing it 5 times. X is 4 because you're tossing 4 heads. And P, your probability of a success, it's a coin toss, so it's going to be 50-50. Doesn't matter even if it was head or tail, same outcome. So this tells you 4 successes, 1 fail, and the combinations thing at the front is just there to say how many ways could you have tossed 4 heads? Because you could have done head, 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 tail, or you could have done head, head, tail, head, head. The order, each of those individual combinations is an additional copy of just doing 0.5 to the 4 and 0.5 to the 1, which is what this NCR term handles at the front. That's just a bit of revision on how binomial works. We don't actually really care about that. We care about the specifics around statistics for binomial, which is the statistics become very quickly simplified. E of x is just NP. So the mean is always just going to be n times p. So if you know the number of trials and you know your probability of success, that's now your average or the expected value. And that should make sense, right? Like if you're tossing a coin 10 times, that means n is 10, p is 0.5. You would expect to get 5 heads, 5 tails. Expected value, 5. Variance is, these do have very specific definitions of how they came about. You don't need to know them. But if you like torturing yourself over that, then it's somewhere in here. Yeah, there you go. Have a read of that if you like math. Otherwise, just take these for granted. Variance is just NP times 1 minus P. And standard deviation, always the square root of variance. So nothing too crazy there. And so in pretty much any binomial experiment, you can find every single statistic because they all just use n and p, which you need for any binomial anyway. So in this case, you've got a jar of 5 white, 3 black, and we're selecting 3 balls out of it. Normally would do things like calculate the probability of X number of black or X number of white, whatever. This time we're doing our statistics. So, first things first, can anyone tell me why this is even binomial to begin with? By referencing like the criteria. Why is this binomial?
You can only like choose either a white ball or a black ball.
Yep, only white ball, black balls. That means 2 possible outcomes. What's the other criteria, and why is this being met?
Is it because like they're being replaced, so there's always going to be 2 outcomes?
So there's always going to be 2 outcomes regardless of if they're being replaced or not. It just means there's, because in 3 selections, you're never going to run out of white and black. The reason why replacement matters is because the second criteria of binomial, maybe it's the third, I don't know. A criteria of binomial is that repeated trials have to be identical. And the fact that it's being replaced means that probabilities are not changing from trial to trial. That's what that keyword's all about. So yes, basically we've identified, yep, things aren't changing and 2 outcomes. That means binomial, hence we can use our simplification, which is just figure out n, figure out p. You do need to be careful what you consider a success. The question will tell you. In this case, capital X is tracking the number of white balls, so selecting a white ball is considered a success. So when you do your P, probability of success, you do it in the context of selecting a white ball, of which there are 5 out of a total of 8, if you were to add up those together. We're selecting 3, so it's going to be n equals 3, p equals 5 out of 8, as we discussed earlier, and then like the rest of that's just bashing it out on either by hand or by CAS. It's basically just multiplication. There's nothing crazy going on there. Anything to clarify from that? Okay. Now, it's really worth highlighting that anytime you have an equation, that equation is what I like to consider bidirectional, which just means, yeah, I've written it that says mean equals NP, but I can rewrite that and say n equals mean over p, or p equals mean over n, just by some algebra. Yeah, just rearranging things. And so one thing that's really worth considering is any equation that you ever have, as long as you have all of the other variables, you can find the missing one just by rearranging that equation. That might sound obvious, like a no duh, but It's worth pointing out that works for any equation. If you have like 3 out of the 4 variables, you can find that fourth. In this case, we're told specifically the mean and variance, and we have to use that to find n and p. Theory of equations says if you have 2 unknowns that you're trying to solve for, you need at least 2 equations to solve those 2 unknowns. Like vaguely, that's the case in a lot of outcomes. You might remember from like polynomial stuff, if you have a turning point, that can give you like your h and k values off the bat. But in most cases, 2 unknowns means you need to have 2 equations. Well, we got mean and variance, so we're going to create our 2 equations by setting the mean and variance equal to 4 and 2, respectively. That gives you 2 equations that have n and p in it, and so you just simultaneously solve. This is fundamentally just linear, even if there's a bunch of variables in it. The actual simplification there is just linear. Yeah, that's that one. Anything to clarify there? Confidence intervals. This will work the exact same way for literally every kind of probability. You're always going to calculate the mean, the standard deviation, and you'll do plus minus some number of standard deviations. Every single time, it's always been 95% confidence interval. And so yeah, you're going to calculate this the same way as always. The advantage is that now that we're talking about binomial, and because it's so easy to calculate these figures, you can really up the n, the number of students. And in that way, when you do your calculation, now the confidence interval actually means something. Like for this one here, a group of 400 people, we get a distribution of 304 to 336. Right, so it's actually fitting within our 0 to 400 without spilling over stupidly like we had for this thing. So increase n really makes this a lot more effective. But how to actually calculate it? Well, first things first, we have to figure out why this is binomial. Yeah, why not? Take a stab at that one again. Why is this binomial? One of the criteria kind of has to be assumed, which is a bit, yeah, that's kind of one thing you have to just sort of get used to, which things would be considered independent. Because like one of the criteria for binomial is that trials are independent. I think anytime you do a survey, you're assuming that results are independent. So I'll give that one away just so you can have that for any time this comes up again. There's one other criteria we need to ensure for binomial. What have I not said? Two outcomes. Binomial. So binom is usually like 2 possible results. If you ever learnt the binary system of ones and zeros, then it should now make sense, right? You've got 2 possible outcomes, a 0 or a 1. In this case, you either attend a public school or you don't. That's the implied dichotomy there. And so for that reason, you can now calculate your mean, variance, and standard deviation using the binomial simplifications. So in this case, P is your probability of success. You're assuming that success is attending public schools because it says to do your interval for people who attend public schools. Variance, once you have that, yeah, it's just same equations as you've seen before. You do need variance to get standard deviation, so you're just going to square root that. And then because it's 95% confidence interval, you want to do plus or minus 2 standard deviations. And so you just plug in everything you know, and that tells you that you are 95% likely that the number of people who attend a public school within any group of 400 is going to be likely somewhere between 304 to 336. So every time I talk to a group of 400 people, I'm 95% confident that anywhere from 304 to 336 of them are going to have attended a public school. And that's that. So that's pretty much it there. There isn't really a whole lot of time to like actually do any more questions on it, but it's very much the same sort of things we were looking at there, which is you can either calculate the statistics because you have n and p, or you can do the reverse, which is you have the statistics, now calculate n and p. So let's see. Is there actually anything looking at doing? Graph. Yeah, here we go. It's in 14b. Well, actually, there is a 14c. Finding the sample size. What's going on there? Oh, no, we did that one already. We'll leave that. 14b. Oh, these might be worth talking about, actually. Sometimes you get a sort of graph like this. This is the graph of a binomial probability distribution. Now, specifically, it's one that had n equals 20, and they had varying degrees of probabilities of success. And basically, the way it works is on the x-axis is the number of successes that you have, and on the y-axis is the probability of those successes occurring. And what you'll find every single time is that they kind of fit this sort of bell curve looking thing, where it sort of rises up, then falls, and then tapers off. Same thing over here, same thing over here. That's a very common type of shape. It shows up pretty much everywhere in real life. In fact, your grades at the end of the year, or even within your classes, whatever SACs or tests you're doing, those are going to be distributed like this. It's pretty much a law of nature that a lot of things are. This is what's referred to as normally distributed, where it has a sort of bell curve effect going to it. That's a fun little thing worth talking about. The center of the bell curve is always the mean. So if you think about 0.2 and 20, if you do 0.2 times 20, you're going to get the 4. If you do 0.5 times 20, you're going to get 10. So the center of that curve will always be the mean. And then depending on how far it spreads out will be your variance. But because it's binomial, mean and, well, p and n are very closely linked together. So it's unlikely you're going to get much more different spreads. All right, that's about it. That's a little bit more than what I was going to say. All right, I'll leave you guys to it. Otherwise, stay behind and I'll clarify whatever you want. Take care.